Hello, this is David Comperator at Lumetrics, and I'm in the lab. Today we are going to measure the changes you see as you add a salt to a liquid. That is something we can measure with the OptiGauge. The setup I have in front of us right now is an OptiGauge Pro pointing at a cuvette. Well, that cuvette has a section where I can put liquids. Right now there's water in this gap here. The gap is about 5 millimeters, and what we're going to do is we're going to monitor the optical thickness, which is apparent in the upper right hand corner. The top number, 6,752 microns of optical thickness, which is the physical thickness multiplied by the index of refraction of the material in that gap. Water's index of refraction is about 1.34. Group refractive index at 1310 nanometers. 1310 nanometers is the measurement wavelength of the OptiGauge. We also put in a red beam so that we can see where we're pointing the OptiGauge, and in fact I'll show you the beam now. There's the beam, and you can see when I block the beam that the signal goes away in the waveform there, and in fact the beam actually passes through the cuvette and the sample, and what we're really reading is back reflections at all the surfaces. Now the only two surfaces we're interested in are the front surface, the interior front surface of that 5 millimeter gap, and the back surface of that 5 millimeter gap. And that's what we're showing here. So here is the front surface of that gap and the back surface of that gap. And in between is the water. And that water's thickness, optical thickness, is 6,752 millimeters. So 1.34 index of refraction for water. What happens if you start to add salt, a salt to that? In fact, I have some sodium chloride, which is plain old table salt. And we're going to start just dropping it in, see if we start to see any changes in that thickness. So here we go, a little bit's going in. Ooh, a lot of it's going in. That's good. We'll look for a big change. We'll look for a big change. So as the cloudy water settles, we lose the back signal for a little bit until we get a good mix, and it doesn't, and the saline isn't as cloudy. I'm going to see if I can stir things up and help that along. I may have went a little overboard with the salt on this one. I might not be able to dissolve it all. We'll have to be a little more careful next time. Yep, I think I did it. I think I did it in. All right, stop. Oh, wait, it's coming up. Maybe. Oh, look at it. It's gonna come. It's gonna pop up. As those undissolved salt crystals settle out and the fluid gets clear, we can see that we're starting to. There we go. We're starting to. Okay, it might take longer than I want for this video, but that's what editing's for. I'll sit here for a second, see if it can catch up. See, the problem is I can't read the optical thickness with any sort of confidence in the accuracy until it settles, because I think it's averaging right now. Yeah, it's averaging 10 measurements. So any one where that peak disappears is averaged in with the other ones, and it looks like it's going to settle in at 6,855. So after a little bit of time, the saline that I've just created has a much different optical thickness than the water. Oh, darn it. It dropped back down. Well, 6,855 is the new optical thickness for this saline. So with a known gap that doesn't change as you're reading it, you can place a different fluid in that gap and correlate and in fact calibrate a optical thickness to the concentration level of salt in solution. Now you can imagine this would be useful if you had a tube with a known ID and fluid, is flowing through it, say in a mixing process. You could actually monitor it in real time in situ as saline is being mixed. Okay, again, this is David Comperator from the lab in Lumetrics, showing you how to use the OptiGauge to potentially measure the concentration level of salt in a saline mix that you're creating.